I recently came across a video on YouTube by a flat earther who was claiming that rockets don't work in space. In this video, I'm going to go ahead and review the other video and point out the things that they got right, as well as point out the things that they got wrong. Now, if any of you are aerospace engineers or are hoping to become aerospace engineers, go ahead and hit that subscribe button. This channel is dedicated to aerospace engineering, education, and software, with the goal of helping you take your aerospace engineering skills to the next level. Let's go ahead and start reviewing that video.
Well, basically it's just impossible. It cannot work in the vacuum of space. It's just impossible. Physically it's impossible.
This is what we call an unqualified assertion.
Physically it's impossible. Yeah.
So, what about all the scientists? Are they all lying, or?
Lying? Really?
Are they all lying, or?
The thing is that we have understood the word scientist wrong. Look, I'm a scientist. I'm a mechanical engineer and I have a master's degree in technical physics. And I work as a research and development scientist.
I would caution you on how you try to establish your credibility. You're just stating assertions and then stating your qualifications, but we haven't yet heard any explanations, experiments, theories, formulas, mathematical models. So it's just coming off as an appeal to authority right now.
Development scientist. But when you say a scientist, you think that these guys are out there and they're just exploring the universe and trying to find the secrets of the universe. No, it's not like that. They pay us to do certain things, certain tasks. And if they don't pay me, I'm not gonna go search those stuff.
Problem here. A scientist is by definition someone who studies or has an expert knowledge on the natural or physical sciences. That, of course, is the Oxford definition of a scientist. And what is science except for applying experimentation and mathematical modeling to understand the world around us, to learn these secrets about how it operates, how it functions? What you're describing sounds more like engineering. Every once in a while in our coursework, we hear that the difference between a scientist and an engineer is that a scientist studies the world around him, while an engineer makes the world around him. Right? The idea that the scientist is just in it to study and understand, while the engineer learns these scientific principles and applies it to making a machine or structure or some device. So it sounds like you might be confusing a little bit science and engineering right here. Now, just because you are in it for the money doesn't mean we all are. Taking this at a higher level, what are we doing having a discussion on finances? Let's leave that to a budget meeting. This is supposed to be a scientific argument to back your claim that rockets don't work in space. I'm still waiting to hear why.
Don't pay me, I'm not gonna go search those stuff. Even if there are some people like me who do think about it, the thing is that since childhood they tell us that the rockets do work and the NASA is sending stuff up into the space, and so you're just programmed since childhood. You're not gonna be questioning that program. And even if you do question that program, people will laugh at you. People will judge you. They think you're stupid. So you end up losing your jobs and friends and stuff. So the scientists, they don't do that to themselves. It's a stupid thing to do. Even if it's the truth, but you just don't do it.
All right, I can't take it anymore. Let's have a discussion on the method for doing science and the method for making a scientific argument. AKA, let's talk about the scientific method. Time to hit the chalkboard.
The scientific method is usually broken down into a couple of steps, depending on whether it's broken down into 4 steps or 5 steps or 6 steps. Doesn't really matter. It always follows the same pattern. The scientific method usually starts with an observation. You notice some phenomena in the world and you don't understand what's happening. As you observe these physical phenomena in the world, it leads you to question how it's operating or what's the driving force or principle behind the phenomena. And so that leads you to your question. To try and answer the question, you have to come up with hypotheses on what potentially could be causing this event to occur, what could be causing it to not occur. And so that's kind of what you're doing when you are hypothesizing. You're trying to rationalize in your head what's going on. So once you hypothesize in your head what could be occurring, you develop an experiment to test that hypothesis. You're trying to determine, is my thinking correct? Is my hypothesis valid? Is it invalid? And of course, there are certain qualifications for your experiment. It's supposed to be repeatable. It has to be able to be proven wrong. The idea is that you're trying to, with some sort of test, determine whether your hypothesis is valid or not. So after you perform your experiment, you look at your data. Did it prove or disprove your hypotheses? You might look at it to say, is this actually proving what I want it to prove? And this is usually kind of summed up or rationalized out in the conclusion when you go over the results from your experiment. After that would be a peer review step where you just get other people in your field to look over your hypotheses and experiment and your analysis of the data from the experiment and just go over your conclusions to make sure that it seems valid. Now my graphic here has it in a circle because, once you come up with conclusions, that might make you observe other phenomenon, and then you can start questioning what's going on there, and it just starts the cycle over again. Now, if you notice, and most people don't, in school, when you're doing a lab and have to write up the lab report, or if you're doing a research paper, the different sections of that paper will actually follow the scientific method. Now, if you're also trying to prove or disprove, and I put those in quotations, of course, if you're trying to provide evidence for or a case for or against something, you normally want to follow the same method. If you're just stating unqualified assertions of this just doesn't work, that's not how science is done or argued. It really just comes off as weak and you don't know what you're talking about. You need to be able to explain the physical phenomena of which you're arguing about. You need to understand any experimentation already done on the subject or have performed experimentation yourself. Then go over the results of that, talking about, from a scientific point of view, the scientific principles behind it. You can't just say, my results are valid, my results are invalid. You need to say why they're valid, right? Show your work, show your math type of a thing. And then in your conclusion is where you can assert things based on the experimentation and observations from before and send it out for peer review. This video is actually making the claim that in science, we're brainwashed to not question the program. We just accept what they tell us. And that's how it works. We just memorize and learn all this stuff and regurgitate it. We're not actually taught to question it ourselves or think differently. But as you look here at the actual scientific method, questioning is built into the method. In fact, questioning is the very backbone of the scientific method. If we observe something we can't explain or doesn't make sense, the scientific method is designed to go and figure out what's going on. The scientific method is what's used because you are questioning the world around you. For instance, if I let go of a balloon filled with helium and it rises instead of falling, that would lead me to question my understanding of gravity, at which point I would hypothesize why the balloon rose instead of fell to Earth like my current understanding of gravity tells me. And so I would come up with some experiments, what's going on chemically or thermally or mechanically to try and understand why the balloon rose instead of fell, all because I found something that does not agree with what I know. Now, to take it one step further, papers being published, trying to get the Nobel Prize, or inventing something or getting your name in future textbooks. These are all highly sought after things. And these are obtained by questioning the current understanding of science. So to say that science teaches us to not question the program or to not question things is really the exact opposite of what's going on.
Now about the whole judging you, thinking you're stupid, losing your friends and family, that doesn't really happen in science. That happens more when you follow crazy conspiracy theories and try and back it up with pseudoscience. It's just not really a thing.
Just don't do it. The reason that you do think that rockets work in the vacuum of space is because of the third law of motion. The third law of motion states it says that for every action there is an equal and opposite reaction.
Yay! Now I'm celebrating for two reasons. The first is that we're actually starting to talk about the science. The second reason is that he correctly identified Newton's third law of motion as the driving principle behind rocket motion. Let's see if he understands it.
An opposite reaction. So it's really easy to test that. Let's put this into action. An action is, for example, I'm going to start punching now. So I'm punching.
All right, let's be very clear about our definitions here. An action, or its cousin, the reaction, used in the laws of motion is a very specific thing. And that specific thing is a force, a push or a pull. So your first use of the word action, as in let's put this to action, means more of let's try an experiment or let's test this out. It's not the same use of the word action as it's found in the laws of motion. Now for your second use of the word action, you said something along the lines of an action is, for example, I'm going to start punching. Now if we're talking about Newton's laws here, for your example, the action is not the punching. The action would be the force that the punch applies to something. That's the action.
So I'm punching and I don't feel any reactions. Do you see reaction? I don't feel any reaction. But then I start punching the wall. I feel the reaction. I mean, you can try it. You feel the reaction. If it starts hurting, and if I punch harder, it's going to bleed, and if I punch even harder, it's going to break my bones.
Just because you don't see a reaction or feel a reaction doesn't mean that there isn't a reaction taking place. Think of a mosquito. You often don't feel a mosquito on your skin until it bites you. That's when you do the Now, since you don't feel the mosquito as it's on your skin, does that mean it's not applying a force onto your skin? We know that it's applying a force. We just can't feel the force because it's so small. It is curious though that you recognize if you punch the wall harder, you'll have a different effect. I wonder why you didn't apply that reasoning to why you didn't feel something in the air.
It's going to break my bones. So it seems like the third law of motion, where in order for you to get the reaction, the equal and opposite reaction, you have to apply your action on something. If it's nothing, then you don't get the reaction.
Correct. The third law describes the interaction of forces between objects. Specifically, if I push on an object, the object then pushes on me. That's the definition of the third law.
You don't get the reaction. For example, if I'm now pushing, I'm now pushing myself, okay, I'm pushing my hand, and no reaction, I don't feel any pushback. But then I push the wall, and I feel the pushback. So, you cannot just push nothingness and expect something to happen. There has to be something.
Run away! All right, so let's look at what we know. So what we know is that air has mass. It's an object. So if you apply a force on an object, due to the third law, it's gonna push back on you. Okay? So we know that. Now this guy, he says that when he pushes he doesn't feel a reaction. Do you know what that means? Now, since he can't feel anything on his hand, that must mean he's not in air. He must be filming in a vacuum chamber. He must be a lizard person, because only lizard people don't need oxygen to survive. We have an actual lizard person here. He's not pushing on air. He must be pushing on a vacuum, because he doesn't feel anything. Because we know air has mass, so it must be in a vacuum. He's a lizard person. I guess maybe there's another option that he's not applying the force on the air that he thinks he is. Or maybe that the force is too small, he can't feel it. But that would mean he doesn't exactly understand what gases are doing. And I thought he had a degree in physics. Huh. Which one do you think is more likely? If you think he could be a lizard person, let me know in the comments below.
I'm now pushing myself, okay? I'm pushing my hand. And no reaction, I don't feel any pushback. But then I push the wall, and I feel the pushback. So, you cannot just push nothingness and expect something to happen. There has to be something.
You assume that if you're punching the wall with the same oomph that you're punching the air, that you're applying the same force onto the wall as you are onto the air, right? You feel that same oomph in your muscles, so obviously you're applying the same force. The problem is that's not the case. You're not applying the same force on the solid wall as you are on the air. And this is why you don't feel a reaction force when you punch the air. Your sensor, your tactile sensor in your hand, your skin, just isn't able to pick it up. And unfortunately, at this time, you can't just go buy a more expensive sensor. Maybe in the future. Also, keep this part of the video in mind later when he starts talking about how a rocket is able to ascend into space by pushing on air.
Let's go ahead and talk about normal forces in a solid, and then we'll compare that to normal forces in a gas. Before we talk about forces on a solid, let's talk about what a solid is. A solid is something that holds both its shape and its volume. A solid does this because the different particles that make up the solid, they don't want to move past each other. They're held in their place by these bonds between the different particles, the intermolecular bonds. This is different from a liquid where they want to slide past each other, or in a gas when they're free to move about and they just bounce around and every once in a while collide with each other. What this means is that if you try to push one solid into another solid, it's going to resist that. They don't want to occupy the same space at the same time. This is because those particles have a strong bond between each other where it doesn't want to allow its particles to move past each other. So if you take your fist and you push it against the wall, there's a force that your fist is applying to the wall because you're trying to make both of these solids occupy the same space at the same time, and those bonds between the different particles do not want to slide past each other. They want to hold on to its shape, hold on to its volume. Now, it seems like you understand this aspect, and most everyone does because we interact with this all day, every day. Whether I'm opening a door or turning a TV on, I'm applying a force on an object, and that object holds its shape. However, in the next slide, we'll cover something that might not be as intuitive, simply due to the fact that we don't interact with it as much. Or rather, when we're interacting with it, we don't consciously know we are. Now let's talk about normal forces in a gas. Earlier we talked about a solid as something that holds its shape and holds its volume. A liquid is something that holds its volume but doesn't hold its shape. Now here in a gas, the gas also does not hold its shape, but what's different about a gas is that a gas does not hold its own volume. We often hear that a gas expands to fit the room that it's in. So this makes gases a little bit different. We have to make sure we understand what's going on with the gas, especially when talking about the force that a gas exerts on objects. So let's talk about pressure both at a small scale and at a large scale. At the small scale, the micro scale, if we look here at the top right, gas has a bunch of particles that are bouncing around and colliding with each other, but it's also colliding with the objects that are exposed to that gas. So if I had a pressure tank that also had, I don't know, let's say someone dropped their keys inside the pressure tank and it got pressurized, that higher pressure in the pressure tank is not only applying this force onto the container, right onto the pressure tank, it's also applying it onto the keys that are inside the tank. This is because the individual particles of the gas are bouncing off not just the walls of the tank, but also the objects inside the tank. Now, when these particles bounce off the objects that it comes into contact with, it's applying a small force onto that object. And that object, of course, has its reactionary force where it's pushing back onto the particle. Pressure is the average that the particle exerts in this collision taken over a certain area. For instance, if I had a 3-inch by 3-inch piece of steel inside a pressure tank, the pressure on that piece of steel would be the average of all the individual forces of all the individual particles hitting that piece of steel. This is why we use the term pressure when dealing with gases and not force, because we're averaging it out over a specified area. Now at the macro scale, we usually use the equation of state or the ideal gas law to explain what the gas is currently doing. And I have the equation there at the bottom, the PV equals nRT. So if we're trying to understand the pressure of a gas, right, the force that it's exerting on a certain area, we have to also take into account the current volume that the gas is occupying. We have to look at N, or the number of moles, how much gas is in that volume at that time. Then you have R, which is the gas constant. So depending on what the gas is it air? Is it carbon dioxide? Is it nitrogen? And then of course T, the temperature. So to understand the force that a gas is exerting on a specific area, right, the pressure, we have to understand all of those other variables as well. That's why this is called the equation of state, right? What's the state of the gas? Now think of all this when talking about punching air and trying to feel a force of it. If you're in a room and you're punching air, are you changing the volume of air in that room? No, the walls of the room stay the same. Your fist is merely moving around in the air. It's not really changing the volume of the air. Granted, there could be a little bit of negligible factors with cracks in doors. We're not talking about that. Obviously, the punching is not changing what gas is in the room. And on a large scale, you're not changing the temperature of the gas. So understanding that, I would ask, what were you expecting to happen? You are trying to increase the pressure, the force per area that you felt on your hand, without changing the volume, without changing the amount of gas, the type of gas, or the temperature of the gas in the room. Were you really expecting a force increase on your hand? Something that you would feel? Now I'm saying force increase because there is currently pressure in that room. We call this atmospheric pressure. That's the pressure we have here on the surface of the earth. We are creatures living at the bottom of an ocean of air. And at the bottom of this ocean of air, it has a typical air pressure of 14.7 psi. Now, there's one other thing to consider when talking about the pressure of a gas. And that has to do when you start adding movement to the equation. Whether that is the gas moving quickly past a stationary object or an object moving quickly through a stationary gas. When you push on a gas and cause it to start moving, you are aligning to some degree the direction of travel of those individual particles. And so what happens is more particles hit the object in that direction of travel than they are hitting stuff out of that direction of travel. Now remember, we're talking 3D space here, so you're increasing the velocity of these particles in one direction, but they still have velocity in other directions. Now you still have to consider how the other particles are moving around the object as well. So it's a little bit more complicated than just thinking, well, I increased velocity in the x direction, so I should see an increase in pressure. No, particles also flow around objects. Now, this whole study of how air flows around objects or the pressures developed on an object in a moving gas scenario is what we call aerodynamics. When an object is flowing through a fluid, as in air, or this fluid is moving around an object, we're entering a complex flow field type of a problem, which often needs the flow field solution, right? This is where the Navier-Stokes equations come into play, and this is where we spend a lot of times as aerospace engineers in aerodynamics. What we try to do is we try and understand the flow field around this object and understand the local pressures on the surface of the object. Different parts of the object have a different local pressure. And so in reality, what we need to do to see the different forces on that object is we need to, using vector calculus, sum up the pressure around the object to determine where the net or resultant force is on that object. And then we could take that resultant force, break it into a component that is acting along the same axis as the flow direction, right? We call that drag, or perpendicular to the flow direction, and we call that lift. Drag being a force that is experienced by the object that is trying to resist its movement.
There has to be something.
But what about if I, for example, in a skateboard and I have a bowling ball, let's say, and I throw it, I go backwards. So
Look, when you are standing on a skateboard and then you are pushing a 15-pound bowling ball, that 15-pound bowling ball has a static inertia. It means it wants to stay static. It doesn't want to move. So when you're pushing that, you're pushing yourself back.
Okay, first off, it's not static inertia. It's just inertia. Inertia is an object's resistance to acceleration due to the mass of the object. This actually comes from Newton's first law of motion, which states that an object at rest wants to stay at rest and an object in motion wants to stay in motion unless acted upon by an external force. So what this means is that an object's velocity wants to stay the same, whether its velocity is zero because it's not moving, or whether it's a positive value. This means that to change an object's velocity, we have to apply an external force to accelerate it. And inertia is the resistance of that object to accelerate. I mention this because whether an object is stationary or moving, its mass is usually not changing. And since inertia is just the resistance to acceleration based on mass, you really aren't going to see a difference between a static and a dynamic inertia. And it's the reason why we just say inertia, not static inertia. Second off, this skateboard example is actually a pretty common example of the third law of motion. In fact, I used a similar example in a video I did for my rocket series. Maybe I'll go ahead and throw a clip from that video here for any of you who might not have heard of this experiment before.
I went ahead and put together an example that I'm hoping helps to clarify how the third law of motion and the second law of motion both explain how a rocket produces thrust. And to really give you a physical example of what's happening, since it can be a little hard to wrap your mind around at first. Now, for this example, let's say it's Friday night and you decide, hey, what better thing to do on a Friday night than go down to my local hardware store and buy a bunch of anvils. Anvils, of course, are these very big, massive, heavy tools. So you go down to the hardware store, you load up a shopping cart full of anvils, and the lines are busy, so you decide to play around for a little bit. So you decide to go ahead and sit on the shopping cart, pick up one of the anvils, and throw it. Now, I know what you're thinking. This is totally what everyone does on Friday night. Now, what's going to happen to you? Let's take a look at it from a third law perspective and a second law perspective. From a third law perspective, we see here on the left, when I'm throwing the anvil, I am using my muscles to exert a force on the anvil. This force that I'm exerting on the anvil would be the action force. And from the third law, we know there is a reaction force equal and opposite to the force I exert with my muscles. The idea being that if I'm pushing on the anvil is pushing on me. And since I'm sitting on this cart full of anvils, it's pushing on me and the cart and all the anvils together in the opposite direction as the force that I threw the anvil. Take a quick second to think about it. Obviously, the anvil is going to move backwards because I just threw it. But what about me sitting on top of the cart? Am I going to sit still? Am I going to move? Why am I going to move? How far am I going to move? Am I going to move as far as the anvil? Am I going to move farther than the anvil? Am I just going to stay still and the anvil is going to move? To understand the motion that would happen due to these reaction forces, we actually need to separate the objects, look at them individually in a free body diagram to see what all the different forces are acting on both objects. Looking at the anvil, there's a weight object that's pulling it down, but we're just going to neglect that for right now. We're not looking in that direction. We're looking at the horizontal direction. If we look at the horizontal direction, this action force that I applied to the anvil would be pushing it to the right. And the only resistive force to that would be air drag, which is probably not going to be that important. So we're just going to ignore it and say that it's so small we don't care about it. To understand the acceleration of the anvil to the right, we use the second law of motion, F equals ma, and use this net force to the right and the mass of the object and determine it's going to accelerate to the right. This is what we already knew. It's pretty intuitive that if I throw it, it's going to be moving in that direction. Now, what might not be intuitive is what's going to happen to me sitting on top of this cart. We know from the third law that when I pushed on the anvil pushed on me and the cart and everything in the cart. So what we have is this force that is pushing on us to the left. We do in real life have some forces that's going to resist this force. For instance, we're going to have friction in the bearings and wheels. Since we're talking about rockets, we're not really going to have these wheels and the ground and all that friction to deal with. So we'll just ignore it here in our example. So really, I'm having this force that is pushing me in the cart to the left with nothing really resisting it. I mean, I got some air drag, but like we talked about before, for this instance, it's very small. Since there is a net force on me and the cart are going to accelerate to the left. Now, when I asked you how far I was going to go if I moved, I was really hinting at this idea that there's a difference in mass between the anvil and myself and the cart and all the other anvils I have in there to purchase. So the anvil is going to go a lot farther than I am in my cart, but I'm still going to move some. Now, what's going to happen if I pick up another anvil and throw it? The anvil is going to fly backwards, and it's essentially going to be pushing me forwards a little bit at a time. Since I loaded up and I've got a handful of anvils in my cart, if I pick one up and throw it, pick one up and throw it, pick one up and throw it, I can essentially start propelling myself forwards by throwing the anvils backwards, right? By forcing this mass to the rear. And this is the idea of how a rocket produces thrust. So when a rocket is burning and creating this jet of combustion gases, it's throwing this mass of gas backwards. Now, the mass of the gas isn't very big. There's not a whole lot of mass there. But the rocket is producing thrust because it's throwing it at very high velocity backwards, and as it's burning, it's throwing more and more and more and more. So it just keeps throwing this small amount of mass at high velocities rearward. And so that's creating a huge momentum, right? Momentum is mass times velocity. It's creating this huge momentum or force backwards. And due to Newton's third law, we know that there is a reaction force of the same momentum pushing the ship forward, and that is what we call thrust. Now there's something else to notice in this example. As I pick up an anvil and throw it, the mass of me plus the cart plus everything in the cart is actually decreasing as well. And we'll probably talk about that in a future video, and maybe even a little bit in the video where we go over the general thrust equation. Just keep that in the back of your mind.
Hopefully now you have a better understanding of this experiment, of this example. The third law comes into play to describe the interaction between you on the skateboard and the big heavy object that you're throwing. Right? As you're throwing this object, you have to use your muscles and apply a force to accelerate it. And as you are pushing on it, it is actually pushing back on you. That's the third law. It's describing the interaction between me applying a force on another object and that object's applying a force on me. Now, if we're wanting to look at the motion of the heavy object that we throw, or the motion of me standing on the skateboard as I get pushed back, then what we need to do is we need to separate the two bodies, look at them individually in a free body diagram, right? We're trying to look at all the different forces acting on me or versus on just the heavy object that we throw. As we look at the different forces acting on the object, we can find out where the net force is going to be. When we threw the ball, the net force was in that direction, so it accelerated that way. However, the force it pushed on me caused a net force on me that way, which is why I would accelerate backwards. This is the idea behind it. Now, I take issue with this part of your video because it doesn't seem like you're completely understanding the third law and that you're somehow trying to use the first law to explain the motion of you moving backwards. Now, maybe this isn't the case, but the way your video explains this example is that you try and define that this object, this heavy object, has what you call static inertia, right? This resistance to movement. And so you're pushing on it, but it doesn't want to move, so you move backwards. You're kind of pushing yourself on something that doesn't want to move. However, this is not how the example is actually working. You do this example, both the heavy object moves and you move as well. That would be described by the second law. The third law is just describing the interaction between me and the heavy object in terms of the forces. I apply a force on it, it has a reactionary force that it applies on me.
You're pushing yourself back. If you think that the third law of motion works in these kind of cases, then you can just throw a pen. Just see if you go backwards when you're throwing a pen. Throw a balloon, throw a light object. And yeah, cool. So you have a balloon and you can push the balloon and see if you go back. Or a ping pong ball. It doesn't happen.
Alright, at this point you either have a serious misunderstanding of the laws of motion, specifically the third law, or you're being misleading on purpose. I'm not exactly sure which one it is. I want to give you the benefit of the doubt, but it's kind of hard right now. Earlier you claimed that the skateboard example worked because you were pushing against a heavy object, but now you're trying to claim that it doesn't work on the light objects. Could you provide me the weight at which the third law no longer applies, right? When it is no longer a heavy object, it's a light object, so it no longer works. What is that weight to you? And what's the physics behind why that weight no longer works? Now you are again operating under the faulty assumption that you are applying the same force on the light objects as you were on the heavy object. Now we know that with Newton's second law, force equals mass times acceleration, if we get a lighter object in here that has a lot smaller of a mass, if you're wanting to have the same force, you have to compensate it for it with your acceleration. So your acceleration is going to skyrocket through the roof. If you were trying to apply the same force on the light object that you were on the heavy object, you have to accelerate it by a large amount. You might actually throw out your shoulder before you're able to get this light object to accelerate fast enough to achieve the same force as you did on the heavy object. This is actually why a heavy object is used in the skateboard example, because for a typical throwing speed you have to exert a greater force on a heavier object, so it's going to exert a greater force on you, causing you to actually move farther in the skateboard. With a light object, you're not able to achieve a high enough force to kind of see as much movement. What's interesting about rockets is that they are not throwing a very massive thing backwards. They are throwing a lighter object, a gas, backwards, but at such high velocity that you get that high momentum, right? You're getting a high force out of it because you're throwing it very, very fast.
It doesn't happen. The same thing when you are pushing a car. You know, have you ever tried it when a car is broken and you're pushing it? At the beginning, it doesn't move. It's heavy, and then after some time, it just moves slower. It got out of that static inertia. It's now moving, so it's easier to push it. It's not that difficult. So in order to get this reaction, you have to push against something. Otherwise, it's not happening.
Again, you're using the same term, static inertia. But as we talked about before, inertia doesn't have anything to do about whether an object is stationary or whether it is moving. Now, as long as the mass is staying the same for an object, whether it's stationary or moving, the inertia is going to stay the same. Now, you can move something out of its stationary position by applying a force and causing it to accelerate, but you can't just push it out of its inertia. The mass will always be there. Now, there is another type of inertia out there that we call rotational inertia. Now, this moment of inertia or rotational inertia is what resists angular acceleration, right? Rotational acceleration. And that has to do with mass as well, but it has more to do with how the mass is distributed around the spinning axis. So you can have normal inertia or rotational inertia, sometimes also called moment of inertia, but there's no such thing as static inertia. Now, I'm kind of curious why you keep using static inertia and where you must have gotten that term from.
Oh no. Oh no. That's not good. That's not good at all.
Now I'm going to go ahead and continue with the video, and I'll come back around to this idea of pushing on nothing, since this is at the heart of his claim, and we'll talk about it in great detail towards the end of the video. And really, it's the only argument he has supporting his claim at this point, and we'll tear it apart towards the end of the video.
Against something. Otherwise, it's not happening. This guy, the reason it goes up is these high velocity and hot gases that exit the exhaust of the rocket engine will push against the ground first, and then it takes off and it goes up. The air down here becomes thinner. But even if it's thinner, the speed of these gases will turn that thin air into a barrier. You know when you're, for example, driving in the highway and you stick your hand out of the window and you feel this pressure, and the faster you go, the more pressure you feel? That's the same thing. Even if your hand is small, when the speed is high, the pressure increases. It becomes a barrier. The same thing in here. It pushes these hot gases and high velocity gases down. Even if it's thin, it still creates a barrier out of them. So as long as there is air or thin air, the rockets do work, but when it goes out in the vacuum of space where there is nothing, then it's nothing. You can push it and nothing will happen.
So the claim is being made that air is going to turn into a barrier. I would love to hear the scientific explanation for how this barrier is made, what's it made out of, at what speed is it made? Is it not made for slower speeds? Is it only high speeds as he's suggesting? There are lots of questions about this idea of a barrier, but not a whole lot of science behind it. As we learned previously in the video, gases allow their particles to move past each other. So since the exhaust coming out of the rocket and the atmosphere into which the exhaust is being expelled are both gases, and we know that gases allow particles to move past each other. I would really love to know what this barrier is he's talking about. Now, it's true that the particles from the exhaust and the particles from the atmosphere are going to collide. There's going to be a lot of collisions, especially with the mass flow coming out of the rocket and the velocity of which it's coming. However, these collisions aren't exactly forming a barrier. I think I know where he developed this idea of a barrier in his mind, and it's really my second contention with this clip you just saw, and that's the idea of sticking your hand out the window of a car. You see, sticking your hand out the window of a car is not really the same thing as the exhaust gas being expelled into the atmosphere. In the case of the exhaust, we have one gas being expelled into another gas. When we stick our hand out the window of a car, we are now introducing a solid into a flow of gas. Now, when you stick your hand out the window of a car, your hand being a solid is going to affect the flow of the air around your hand, right? This is the whole idea behind aerodynamics, is understanding the flow that develops around a shape when you stick it into different flows of air. In aerodynamics, we would actually call this a blunt body. We've got this nice big old flat area facing the oncoming flow of air, so it's going to be very draggy. So that force you feel on your hand is actually the drag that's being developed, because this hand, this solid, is affecting how air moves around the object. So this pressure you feel on your hand is the increase of pressure on your palm side of your hand and the decrease of pressure on the back side of your hand due to the way that the air is flowing around your hand. You can actually play with it a little bit. If you bring it horizontal, you can actually start increasing the angle of attack of your hand or decreasing it, and actually feel the air pushing your hand up and down. But really, this is an aerodynamic situation. There's not any weird barrier being created of the gases, right? My hand is a solid. It is the barrier.
But when it goes out in the vacuum of space where there is nothing, then it's nothing. You can push it and nothing will happen. This is easy to test actually. Look, you can get a simple drone and just put it on the ground, accelerate it so it lifts up from the ground and hovers at 20 centimeters.
So normally I just leave a little bit of the clip in beforehand so you know that I'm not leaving anything out. However, I left a little bit more in this time, just to give you a little laugh, as he claims that a rocket has to push against the air to move, and then he pushes against the air and says, nothing, there's no force here. But that's the same thing the rocket is pushing against, according to him. So I just left that in there for your enjoyment. I think we left the science behind, guys, as in this experiment, he's trying to show how rockets work in space by showing us an experiment in the atmosphere, not including rocket propulsion. So the manner of propulsion is different and the environment is different, but this test is supposed to prove something about that propulsion and that environment having nothing to do with either of them. Yeah. This would be like me telling you, let me show you how to make brownies in the oven by making Easy Mac in the microwave. They have nothing to do with each other. Actually, they're making me kind of hungry. Maybe I'll skip this experiment and go make me some mac and cheese. It's got more to do with rocket propulsion than this experiment does.
Easy to test actually. Look, you can get a simple drone and just put it on the ground, accelerate it so it lifts up from the ground and hovers at 20 centimeters. Do not touch the accelerator anymore. Just put the cardboard sheet under the drone and just lift it up. When you lift it up, the drone starts coming up also, and it maintains the same 20 centimeter distance between the bottom of the drone and the sheet. And the moment you take the sheet out, you take it away, the drone just drops down, hits the ground, and the hitting the ground happens due to inertia.
and with the misunderstanding of inertia. The drone hits the ground because the lift force generated by the propellers is not enough to overcome the gravitational force of the Earth pulling on the drone. This creates a net force downwards, and so the drone actually moves towards the ground. Now it hits the ground even with the increased lift due to the ground effect that we're going to talk about here in a minute. Even with that boost, it's already accelerating fast enough, it has enough momentum that it's not able to stop in time before hitting the ground. However, it is able to recover with that increase in lift due to ground effect we're about to talk about and balance itself out. The inertia of the drone, since it was at rest while it was hovering, wanted to keep it at rest or hovering due to the first law of motion. However, the net force of gravity, according to Newton's second law of motion, is what actually pulled it down to the earth.
The ground happens due to inertia. Hits the ground, comes up and maintains the 20 centimeter distance. So based on these observations, based on what I just showed you, pushing, punching, and the drone, which I can show you actually, we can go outside and I can demonstrate this. It's impossible for the rockets to work in the vacuum of space. It just doesn't happen.
Now remember that his punching and his pushing showed a serious lack of understanding of how gases work, the pressure that's developed by gases, and aerodynamics of solids in gases, as well as his experiment testing neither the equipment nor the environment.
It just doesn't happen. The third law of motion happens when you apply your action on something and that something can react to you. When there is nothing, there is no reaction. Simple as that. Yeah. And the thing is, many people say that the rockets don't work in the space because there is no air. No, you're just misunderstanding it. They're carrying their own liquid fuel and they're carrying their own liquid oxygen, so they don't need air. That's not the problem. The problem is this pushing act that you have to push on something.
Even though this guy has a lack of understanding in a couple areas, at least he understands that a rocket brings its own oxygen, and that's why it's able to burn in a vacuum. Now, believe it or not, there are some people who think that you can't burn the fuel, the rocket fuel, in a vacuum. These people probably have never heard that you actually carry oxygen with your fuel in a rocket. So we at least have to give this guy props for that he understands that. Though it's curious why he thinks we would go to such great lengths to carry oxygen with us if we never leave the atmosphere.
Maybe the rockets don't actually carry oxygen. Maybe they have secret inlets where they suck air in from the atmosphere. Maybe the rockets carry oxygen because they are seeding the ozone layer. Why else would they carry oxygen on board if they can't leave the atmosphere?
Oh, sorry, I caught the conspiracy bug there for a second. Whew. Let's keep going.
The problem is this pushing act that you have to push on something.
So you will say that they don't move. They cannot move up in the outer space.
When you're in a vacuum, no, this doesn't produce any thrust.
Even if it's like it's producing its own fuel, it wouldn't move.
It wouldn't move at all. Because as I said, you have to push against something in order to feel that reaction. And back here is a vacuum now. I mean, earlier is a vacuum in the space. So there's nothing to push against, and done. It's just not happening. So yeah, we can actually go outside and try the drone thingy. So I'm not a good pilot, so I have to try to balance it first. But let's try our best. Okay, there we go. So as you can see, I'm not pushing the gas anymore, and we go up. You see, I'm not touching the gas. And then it comes down. You go up, as much as you want, and there you go. And the 20 centimeter is maintained, and then we go up again. You see, it means something to push again, otherwise it drops. Yep, simple as that. Based on this, you can see rockets just cannot work in the vacuum of space. It's done. There is nothing you can say about this. It's over.
Nope. Ground effect. Oh, you wanted a better explanation than that? To the chalkboard.
So let's talk briefly about ground effect. Ground effect, as you can probably guess from the name, would be the effect that the ground has on your lift. When you get close to the ground effect has a tendency to increase the lift and decrease the aerodynamic drag. This is due to an increase in pressure below caused by the change in flow of the mass moving through your propellers, but it also reduces the wingtip vortices. These wingtip vortices are losses, so by reducing this, you are reducing the losses that you normally experience. Now, this cushion effect is also something that you can see in hovercraft where they're blowing air underneath them to create this cushion of air. It's pretty similar to that. Now, for your example, the cardboard, when you hold it up underneath the drone, is acting as the ground, causing a ground effect situation. So it's able to balance itself out slightly above the ground because it has an increased lift due to ground effect. When you pick up the cardboard and you help the drone rise up in the air because you're holding this ground, this cardboard underneath it, you're essentially moving the ground. And you can easily see this is the case. When you remove the cardboard, it leaves the ground effect state, goes into a normal flight situation, but the lift isn't enough to overcome the weight of the drone, and so it falls back down out of the sky. So as you can see here on the left, when I have the normal lift that the propellers are generating added to this extra boost that the ground effect is giving us, it's able to balance out the weight, and so there is no net force, there's no acceleration, it's able to hover where it's at. However, you remove the cardboard out from under it, and it no longer experiences this boost in lift due to ground effect, so it's only left with this lift from the propellers that it's generating, which is not enough to overcome the weight. And so now we're in a situation where there is a net force on the object, and it's going to cause it to accelerate in the direction of this net force, and that would be downwards. So not only is this experiment not talking about rockets nor talking about vacuums, but you're also misunderstanding what is actually happening in your example.
So we reached the end of his video, but I've still got a couple more things to cover. Essentially, his claim that rockets don't work in space was backed by an incorrect understanding of gases and gas pressure, an incorrect understanding of aerodynamics, an incorrect understanding of the laws of motion, as well as an experiment that had nothing to do with rockets or a vacuum. However, I want to cover a few critical issues with the idea that a rocket pushes against the atmosphere in order to develop thrust. The issues we will go over will show why this theory that rockets push against the atmosphere fails to correctly model or correctly describe the actual events, the actual phenomena of rockets and rocket propulsion. The reason it fails to describe and model, of course, is because it is an incorrect theory. It is wrong. It does not match the physical world.
All right, let's go ahead and talk about the first problem with this claim that a rocket needs to push against the ground or the air to move. The claim is stating that the action force would be the exhaust gas pushing on the atmosphere and the reaction force being the atmosphere pushing on the exhaust. However, this leaves out a force that is used to accelerate the exhaust gas. The exhaust gas, of course, has mass. It's gas. It's an object. It is not massless. So it's going to follow the laws of motion. Now what we see is that this gas inside the combustion chamber of the rocket has a relative velocity of 0. Now I'm saying relative because the entire rocket vehicle, right, the stuff that's wrapped around this rocket engine, might be moving. It might have a velocity. And the difference between the exhaust gas velocity and the vehicle velocity is essentially 0. Now, as the gas flows out of the nozzle and exits the rocket engine, we see that this exhaust gas now has a very high velocity. So we see that there is a very big difference between the velocity of the exhaust gas leaving the nozzle and the velocity of the exhaust gas in the combustion chamber. Now we know, due to Newton's second law of motion, force equals mass times acceleration, that if we have a mass and the exhaust gas is a mass, it's a gas, there are particles and molecules, and that has mass. So if we have this mass that accelerates, there must have been an external force applied to that mass. So we see that the mass of exhaust gas has gone from a relative velocity of 0 to a relative velocity of far greater than 0. There is some force that has been applied to the exhaust gas to cause it to accelerate. Now some will try and say, well, it's the pressure of the gas. Pressure, as we've learned before, is the normal force that the gas exerts on another object, not an external force moving the air. What we have here is we have acceleration of the mass of air. There is an external force being applied to the air, causing it to accelerate. Now, the reason that it is left out of the other theory, right, this theory that a rocket needs to push against the atmosphere or the ground, is that if there is another force taking place inside this rocket engine causing the gas to accelerate, then there must be another reactionary force pushing back on the engine. And if that's the case, that would be providing thrust, and ah crap, now the rocket's not pushing against the atmosphere anymore. Now that's why they try and leave this force out or try and discredit it, say, well, it's just the pressure, not understanding that the actual gas is accelerating due to an external force being applied to it. So let's look at what's actually going on inside a rocket engine. The rocket engine begins by converting the fuel's chemical energy into thermal energy when it combusts the fuel. We're burning the fuel and it's turning into heat, it's turning into pressure. This thermal energy is then converted into kinetic energy of the exhaust gas by the nozzle. This nozzle is usually a convergent divergent nozzle, and it's going to have the effect of reducing both the pressure and the temperature and increasing the velocity of the exhaust gas. Now, the nozzle is what pushes on the exhaust gas to accelerate it out the back, and of course the reaction is that the gas also pushes against the walls of the rocket, and that's what produces thrust. Now, there are those people who want to claim that the exhaust gas is just somehow leaking out due to its pressure, or sometimes you'll hear this idea of a free expansion of the gas. The problem with both of those is that they are forgetting the nozzle. The nozzle is a flow restriction. You can't have free expansion if you're having a flow restrictive device in the flow. And the nozzle is a flow restrictive device. It creates a choked flow condition where the amount of mass that is able to flow through it is regulated. This flow restriction means that there's a pressure buildup upstream in the combustion chamber and that there's an acceleration and a high velocity at the exit of the exhaust gas. Due to this flow restriction, you cannot say that it is a free expansion and that the gas just leaks out. And if it doesn't just leak out, then you need to have a reason why the exhaust gas accelerates from 0 to many times the speed of sound. And that requires a force. You need to push on that gas somehow. And then when the gas pushed back on you, you develop thrust. All right, let's go ahead and talk about another problem. And this problem is that the rocket and the exhaust are traveling in the same direction as viewed from a stationary observer on the Earth. Now, when talking about the relative velocity that the exhaust leaves the rocket, the effective exhaust velocity is really, when it comes down to it, driven by the choice of the chemicals used in combustion. If you choose something like black powder, it's going to be around 2,000 meters per second, versus if you're using like a liquid oxygen, liquid hydrogen, it's going to be around 4,400 meters per second. Now, there might be some slight variation due to the manufacturing of the rocket engine, but these values are pretty typical and they don't really fluctuate that much, which is why it's used a lot of times with the mass ratio to do some back of the envelope calculations. You can think of the mass ratio as the ratio of the mass of the rocket when it's fully loaded versus when it's got an empty tank. Now, both the effective exhaust velocity and the mass ratio are used to create the plot that you see here on the left. This, of course, is using the Slifkowski rocket equation. And so we're able to calculate what the rocket vehicle velocity will be based on the effective exhaust velocity and the mass ratio. Of course, if we use the final mass ratio, we can determine what the final velocity of the rocket will be. So let's look at a quick example. If we take the space shuttle that has a mass ratio of about 16, and because it's using liquid oxygen, liquid hydrogen, it's going to have an exhaust velocity around 4,400 meters per second. So if you look at it on the chart, I marked it there with a star. It means that the final velocity of the space shuttle is around 12,000 meters per second. That's pretty dang fast. So what does this look like to someone who is just standing on the Earth? So if the rocket were to zoom past our stationary observer, let's say it's traveling from left to right, the stationary observer would see that the rocket was traveling at 12,000 meters per second past him. The effective exhaust velocity is 44,000 meters per second out the back of the rocket. This is a relative velocity. It's relative to the velocity of the rocket engine, which means that if the rocket is traveling to the right 12,000 meters per second, and the exhaust has a relative velocity of 4,400 meters per second to the left, in reality, as the gas exits the nozzle, it's going to be traveling to the right at 7,600 meters per second. That means to a stationary observer, both the rocket and the exhaust coming out of the rocket are traveling to the right. Now, if we were to go back to the punching example, imagine first placing your fist on the wall, not punching the wall, just placing your fist against the wall, and then quickly pulling your fist back. How much force did you feel that your fist exerted on the wall? In reality, you shouldn't feel any because it's going the wrong way. Before, we were able to apply a force to the wall because we were punching into the wall, but as we punch away from the wall, we're not able to apply a force on the wall. So the problem, and my question to you would be, if both the rocket and the exhaust are traveling in the same direction as observed by someone just standing on the ground, then how is the exhaust pushing on the atmosphere? The problem is that the exhaust velocity is going in the wrong direction to be applying a force to the atmosphere. So if it's going in the wrong direction and is unable to push on the atmosphere won't be able to push on them. There's no action force, so there can't be a reaction force. And so this creates a problem if you think that it's pushing against the atmosphere or against the ground. Since they're traveling in the same direction, you're losing your action force. Now, there are some other flat earthers or conspiracy theory people who are saying that it's not possible for the rocket to travel faster than the exhaust that comes out of it. There's a video I saw recently on YouTube that was making this claim. I'm going to go ahead and cover that in my next debunk video, so stay tuned for that. Now, another problem has to do with the exhaust speed versus the speed of sound. But before we talk about the problem, let's just have a quick refresher on the speed of sound. Sound is actually a pressure wave that travels through the air. This pressure wave actually acts on our ear, which is why we're able to hear things. And that wave actually has a speed at which it can travel through air, a maximum speed. It has a speed limit. This speed limit is called the speed of sound. It is the maximum speed that a pressure wave can travel through air. We often call this Mach 1, where the speed of the pressure wave matches the speed of sound. The speed of sound depends on the type of gas and the temperature of the gas, as we see in the speed of sound equation here, right? Speed of sound is equal to the square root of gamma RT. When talking about rockets, rockets can either be in a subsonic condition, a sonic condition, or a supersonic condition. If we looked at a stationary rocket, if it would send out pressure waves, we would see that it would just travel outward from the rocket, traveling equal distances in all directions since the rocket is stationary at Mach 1, or the velocity of the rocket divided by the speed of sound is equal to 1. Meaning that both the velocity of the rocket and the speed of sound are the same. This means that the rocket is traveling in one direction at the same speed that the pressure waves that it is creating are also expanding out into the atmosphere. If you think back to the kinetic theory, where gas is just a bunch of particles that bounce off of objects, something traveling at the speed of sound means that when a particle comes and bounces off of an object, both the object and the particle are traveling at the same speed in the same direction after the collision. This has the effect of making the pressure waves stack up against each other as the exhaust gas is expelled from the rocket. This stacking up of the pressure waves is going to create a sharp discontinuity between the air upstream, which hasn't seen the object yet, and the air downstream, which has seen the object. This is what we call a shock wave, this stacking up of the pressure waves. Something similar happens when you travel faster than the speed of sound. If you think back to the kinetic theory, if a particle of air bounces off an object, the object is actually traveling faster than the particle when it bounces off. So you're still going to be seeing some of this stacking up of the pressure waves, and we do see some oblique shocks start to form. However, something very interesting happens. Now, normally because the speed of the object is not traveling faster than the little particle that bounces off of it, the particle that bounces off of it is able to transmit information about that object upstream of the object. So this is why we would see the flow start to move its shape before the object actually interacts with it. However, when you start going above the speed of sound, then the object is traveling faster than those particles can transmit the information upstream. And this is why you develop very hard, very dramatic shocks. So let's go ahead and start looking at how this could pose a problem. All right, so according to your claim, the exhaust gas leaves the rocket, pushes against the atmosphere or the ground, and then the ground or atmosphere then pushes back against the exhaust gas, and that pushes the rocket forward. However, one of the big problems with this is how is the force that the atmosphere or the ground is applying on the exhaust gas being transferred to the rocket? The exhaust gas isn't bolted down or taped or glued to the rocket. So the force that the atmosphere or the ground exerts on the exhaust gas must also be passed from the exhaust gas to the rocket. However, there is a big problem with this. You see, the exhaust gases are exiting the rocket at a Mach number much greater than 1. So the exhaust is traveling much faster than the speed of sound. The speed of sound, of course, being the maximum speed at which a pressure wave can be propagated through air. So this means that the exhaust is leaving the rocket faster than a pressure wave can travel through air. If the object is traveling faster than the speed of sound, that means the object will be traveling faster than the fastest possible speed that particle can bounce off the object. So the gas is just traveling too fast to allow pressure to be transferred upstream, right? If the exhaust is exiting at greater than Mach 1 to the right, And the fastest that the atmosphere can push onto this exhaust gas is the speed of sound going to the left. That means that this pressure cannot travel upstream. You can think of this as a fish trying to swim upstream, where the river is flowing fast enough that it's just washing the fish downstream. The fish can only swim so fast, but since the river is moving faster than the fish can swim, the fish is getting swept downstream. The same thing is happening in the exhaust. The effect of the atmosphere on the exhaust gas, as long as those exhaust gases are traveling faster than the speed of sound, cannot travel upstream fast enough before they are swept downstream. This means that even the next atom over after the exhaust leaves the nozzle cannot affect the next atom upstream before it is swept downstream in the exhaust gas. This means that once the exhaust gas leaves the nozzle, it can have no effect on the rocket. The exhaust gas is traveling too fast. And so what this means is that even if the ground and the atmosphere were pushing against the exhaust gas, the problem is that the exhaust gas that is expelled from the rocket is traveling too fast to be able to make that force push on the rocket. And so the rocket is unaffected by the exhaust gas after it pushes it out the nozzle. And let me just go ahead and add this on here. The actual effect of the atmospheric pressure on the rocket is that it decreases thrust. If you look at the general thrust equation, you'll see that thrust is developed primarily by the mass flow being expelled out of the rocket at a certain velocity. However, there might be a pressure differential between the exhaust at the exit and the atmospheric pressure. And depending, of course, on that pressure differential, the atmospheric pressure actually wants to decrease the thrust. So not only is the atmospheric pressure not producing thrust, it's actually hurting the thrust that is produced. So it's the exact opposite of the claim that's being made. So I also have another question for you. How high is space? Now, something that's not really well understood or heard by the general population is that the definition of where space begins is not universally accepted. There are different heights at which space begins, depending on what definition of space you use. For instance, the US military and NASA use a height of 50 miles as the starting point of space. So anyone who goes above 50 miles is deemed an astronaut by them. Now, 62 miles up is where a lot of the international definitions come in, right? The definitions that you would see in like international treaties. This comes about by the Kármán line, where it's the calculated altitude at which you would have to travel faster than the orbital velocity to achieve lift using wings, at which point wings would be useless because you're traveling fast enough to be orbiting the Earth. So if that's your definition of space, then space begins at 62 miles up. A 2009 study by the University of Calgary was looking to determine when the atmospheric winds, or the effect due to this atmospheric wind, are overcome by this idea of the solar wind, or rather when the effects of space overcome the atmospheric winds, and they determined that that's at about 73 miles up. If you want to define space as being where you completely escape Earth's atmosphere, right? You are no longer in air no matter how thin it is. You have to go up to 600 miles. Now keep in mind the International Space Station is up at 250 to 270 miles, whatever it is. The Hubble Space Telescope is up above 300 miles, like 350, 360. You'd have to go another 300 miles past that to escape the Earth's atmosphere, where you're out of the air completely no matter how thin. So my question to you is, where does your space begin? And I think this is a pretty valid question, right? You're claiming that rockets push against air when they get higher up, and that eventually they'll reach a point where the air thins out so much that they're not able to push anymore on the atmosphere. And this is really a secondary question, where the primary question is, what is the maximum altitude a rocket can reach according to your theory? When does the atmosphere become too thin that this quote-unquote barrier can't be formed, or there's no longer something to push against? Let's see the math. Show me where rockets can no longer work and why they can no longer work due to the atmospheric pressures versus the pressures in the rocket, the velocity of the exhaust gas, and the temperature and combustion. Let's see some principles of physics and science. Let's see some math. Let's see some models. Let's see some equations. Let's see some numbers.
Alright, that's the end of my video. This was kind of a new format, a new type of video that I've done. Go ahead and throw it in the comments. Let me know what you thought, if you liked it. Let me know maybe if there's another video you want me to review / debunk. Other than that, check out the other videos on my channel. My channel is dedicated to aerospace engineering and helping those who are or wish to be aerospace engineers take their skills to the next level. So go ahead and subscribe if you're one of us AE guys or want to be one of us AE guys. Thank you. Hope you enjoyed the video. I'm afraid I have bad news. With these kind of grades, I really can't recommend that your child move on to the next grade. I'm afraid we're going to have to hold them back a year.